Hello and welcome again. We're looking at section 2.17, just going over some volume and surface area ideas that we've looked at a little bit before. But so recall that volume is just the a measure, the amount of 3D space an object occupies. The units for this kind of thing we've seen already. Cubic inches, cubic lengths in general, cubic feet, cubic meters, cubic centimeters. It comes up a lot. Also known as cc's, also known as milliliters. And that is a good connection to the other type of unit we use for volumes, other types of units. We use units like, well, milliliters, or just liters, gallons, also cooking volumes, cups, ounces, things like that. We're going to focus mainly on our cubic lengths, and we get the word cubic inches, cubic feet from the fact that a cube that's an inch on all three sides, an inch by an inch by an inch, is going to be called a cubic inch, inches cubed. So yeah, surface area on the other hand is the area occupied by the surface of a 3D object. So the area basically on the faces or surface, exterior surface of a 3D object. And the units on this are going to be our standard units for area, length times length or length squared, like inches squared, feet squared, meters squared, etc. So we're going to look at a few formulas here and kind of talk about how we get them. So let's start with a closed box, basically a box that has length, width, and height. We'll just call it length, width, and height. The volume of this is just going to, as you'd expect, it'd be length times width times height. So if it was 4 by 5 by 2, 4 by 5 by 2, 4 feet by 5 feet by 2 feet, well, that'd be 20 times 2, 20 times 2, which is 40 cubic feet. The surface area, on the other hand, is the sum of all the faces of this closed box. So you'd have like the area of the bottom face. Well, that would be length times width. But the area of the top face is the same as the bottom face, so you just have two of those. So we have the up face and the down face. And then you've got the area of the front and the back, I guess. Well, that's length times height, L times height, L times H. But there's two of those. There's the front and the back. Both of those are length times height. And finally, the right and the left faces are going to be width times height each. So there's two of those. So I'm just showing you this just so you can see how you could derive these formulas for yourself just by thinking about what each of these, what these shapes are made of. Some formulas you just got to learn and just memorize, and that's fine. But I don't necessarily memorize the surface area of a box. I just do what I just did just now. It just ends up getting quicker as you do it more. The next shape we're going to talk about is the cylinder, and you can derive this one as well if you think about it. A circular cylinder, I should say, or what we often call a right circular cylinder, because it's a nice perpendicular It's perpendicular to the ground, I guess you could say. And it has a radius of that base of the cylinder of r. Well, the volume of this, if I just think of the whole base as one big area, the volume of this is just the base, that area of the base times height. Imagine that base is pancake, and you're just stacking a bunch of pancakes up to a height of h. You just have pancake after pancake after pancake, and eventually you'll fill up the cylinder, right? If you think of it just as an area of a base, then it doesn't even matter that the base is circular. You can use this formula for any cylindrical type extruded kind of shape from a two-dimensional base. So in this case, that area of the base is the area of the circle on the bottom, pi r squared. And so that's the volume of a cylinder. Now, oh, by the way, you can kind of see this base, this capital B, which I'm gonna write area of base. You can see that in our formula for the closed box. The area of the base of our closed box is length times width. And you multiply the area of that base times height, you get base times height. You get the area of the base times height. So you get the same formula. So in some sense, a closed box is a square-shaped cylinder. Now the surface area of a cylinder is a little bit more tricky. But you can think about it. First of all, the top and bottom, the faces, the top circle and the bottom circle, that's pretty straightforward. You're just going to have a pi r squared for each of those areas, and there's two of them. And then we have to find the area of that outside. As if this is like a Campbell soup can, and you want to find the area of the label of the soup can. Well, let's draw a picture of that and we can kind of see what's going on. I have to be careful how I draw this. Imagine you took off that label and unwrapped it, and you got the top circle and the bottom circle. I just want to include those just so maybe we can see what the shape of this label is. Well, it is a rectangle, right? Well, the one side of the rectangle is its height. The other side of the rectangle we need to figure out. If we knew the other side of the rectangle, we could do just length times width or whatever, and find its area. Well, we need to figure out what that length of that is. Well, if you imagine this top cylinder rolling around, going across here, by the time it gets over here, it's gone one full rotation. In other words, the label wraps one rotation around the can. That's what labels do. And so that means this side here is the circumference of the circle, which is 2 pi r. So now we know this area is just 2 pi r times h. And that's the area of that entire cylinder. The next thing I want to talk about is a cone. Well, the cone is kind of, or in this situation, technically a right circular cone. This shape also includes pyramid kind of shapes too, but we'll stick with a cone for now, and then we'll kind of see how it extends to pyramid shapes. So again, we have this base that I can call capital B. The area of that base is capital B, and that circle has a radius. And there's two other pieces of information we'd like to have here: the height, the perpendicular height of the cone, and also the length of the side, which I'll call S, which will stand for slant height. It's not to be confused with the actual vertical perpendicular height. It's the slanted length along the side. For a cone, and there's not an easy way to just derive this one without doing some trickery, but you can imagine a cone is still part of a cylinder, right? And so it's going to be a fraction of a cylinder of the same height. Well, that fraction happens to be, in this case, a third. 1/3 pi, well, I'll write it this way. 1/3 the area of the base times the height. And in this case, it's 1/3 pi r squared h. The surface area, on the other hand, is a little trickier. We still have that pi r squared circle on the bottom, so that's still pretty easy. And then we want to add to it basically the area of the outside of this, the side of this cone. If you imagine a paper cone you get when you get a snow cone, if you've ever unwrapped those cones, you know that they unwrap into a shape kind of like this. Looks kind of like that. Well, this area is part of a bigger circle. And I could get into the details of how we would derive this, but maybe I'll save that for another time. But the upshot of this is that this length here, after you unravel it, after you unroll the cone, this length here is the slant height of the cone. And the length of this arc here is just the circumference of the cone, which happens to be 2 pi r. Turns out that part there is pi times r times s. That's what this is. You can think about that, but I'll talk about that later if need be. Last but not least, we have a sphere. Sphere is, as you'd expect, it's a three-dimensional ball. Oops. With a radius of r. And again, its volume this is another thing you just memorize. I would need probably calculus to prove this. 4/3 pi r cubed is the volume of a sphere. And again, you memorize this, or you'll be given it. You'll have access to it on quizzes and tests, so I'm not too concerned about it. And the surface area, really cool fact about the surface area of a sphere, it's just if the area of this equatorial circle, the circle at the equator of the sphere, that area is pi r squared. Well, the surface area of the entire sphere is just 4 times that. That's kind of neat. I think that's kind of one way I remember it too. It's just neat that the area of the sphere is just 4 times the. You'd think it'd be some weird fraction or maybe another pi would be involved in that, but nope, it's just 4 times the area of that cross-sectional equator. Pretty neat. So that's it for the formulas, and I'll maybe do another video on some problems. But for now, see you next time.